All right, I think we can maybe soon start. We will start maybe with a couple of minutes early so that we can introduce people and so on. And we know that also we have the meeting or the entire event will be recorded. So afterwards, everyone will also have the possibility to check it online, to attend it again or to see it again. Also, we have potentially some colleagues online. That's looking forward to start. So I just wanted to say hi to everyone. My name is Nikolai Dimitrov. I'm from DTU Wind Energy in Denmark. And here we have some other colleagues and partners from the Hiperwind project. That's Suwan Do from EDF, Emmanuel Avion from EDF also. Then we have Stefano Marelli from ETH Zurich. We have Nathan Buiton from IFPEN. Alexis Croissant, right? From IFPEN also. And then we have Clement Chaquet from EPRI. And we have a few other partners in the project. You'll find out that unfortunately not everyone could be here right now. Some, couldn't simply travel. Others, have a vacation or many things. But overall, we have. I think I'm looking forward to explaining more about the project. I'm just trying to use a couple of minutes to make sure that also people that expected to be here online at 4:30 that they don't miss too much. But we can then maybe in the meantime start with a small overview of the outline of the event. So we already had the first part. I hope you enjoyed some coffee. I know we've had most likely 2 days enough coffee intake, but there was a little bit more here. I hope that was also nice. I hope you also managed to maybe get a couple of discussions going, and then now I'll use about 40 minutes, maybe up to 45 for the project overview and the highlights. I will also, you will see that there is link to online poll, so you can actually, both you and those that are online could maybe ask questions. So there will be both questions to this presentation, but also we will have a full interactive poll session later where I will ask you a few questions as a feedback. Then also in the meantime, we also have statements by partners. So it's not now in the first 40 minutes, it will be mostly me talking so that we kind of get the entire project very quickly, get a quick introduction to an overview of all the results. And but then we want to see individually what each partner thinks as takeaways from the project. And then finally, once we have passed this and passed the interactive poll session, we'll have a few minutes with 45 minutes with discussion where I would say we try to do it as a panel. Maybe we can even move the chairs. I don't know how it works, but we will then we can just discuss and have any questions from the audience, both here and potentially also online. So I think if any colleagues are listening or seeing the online session, if there's any chat session that we say, oh, we don't hear anyone, just please warn us. And also thanks for other colleagues from DTU, Estelle and Simon for going around, and also some other partners like Raja from Ukraine. So, well, thanks again, everyone. And now we can, I think, start with the main presentation. Is that fine with everyone already? Yeah. So we start with the overview of the project. Let's try to walk you through the goals, through what were the objectives, and what are the actual type of actual scientific progress we've made into the project. What are the results? So this will also have a few steps. First, I actually want to show you who the team, what were the overall objectives of the project. Then highlights of some specific technical results. Then also what is the impact, or at least what we think we expect the overall impact of the project will be. Some tools, because I think also one important types of impact or ways of using the results is to have tools. And then finally, with these partner takeaways. So the specific, opinions or let's say experiences by partners. And maybe you may see, I think on most of the slides, you will see this number, which is if you go to menti.com, I hope it's active and you can already try to ask questions. So for this part, you will get also another chance to ask questions for the panel session later. But now this is more if you have some specific questions to the presentation. So there's two types of questions we're going to use. All right. So what's Hyperwind? I would say maybe you have seen in the name, but the name is really about it's about uncertainty, and also I think I need to mention that it's actually a project funded by the European Horizon 2020 program. This is sponsored by the EU. I think it's really important to state how the project is funded, and so the name is Highly Advanced Probabilistic Design and Enhanced Reliability Methods for High Value Cost Efficient Wind. So we will talk about probabilities, uncertainties, reliability, and how can you use this information to make a cost efficient wind energy. Now, going back to this concept, we start with how the offshore wind turbines are designed now, and then we want to introduce or to handle uncertainties into this modeling chain. And then this starts with looking at the environmental conditions, then also improving the loads, going then to so-called, when you know the environmental conditions and the loads, you can look at better reliability assessment or using this information to reduce uncertainties wherever possible and improve design. And then based on that, you may want to also see if you can afterwards optimize the design or reduce costs in other ways once you have managed to, let's say, to have this improvement of the modeling chain. So uncertainty is key word because in any of these stages you want to actually quantify and reduce uncertainty, or use the knowledge in order to improve any ways the models that you have. So when we say uncertainties, why do we think that it can actually lead to any improvements in design? This is really the hypothesis, which I would think that around half or even more than half of the project activities were based on trying to verify this idea or to demonstrate how you can actually achieve this. So we start by thinking when you have high uncertainty, you normally penalized or your design is suboptimal because you need to use into the traditional design, you need to use safety factors. And so the higher the uncertainty, the bigger the safety factor normally, or that's at least the expression of uncertainty it's in safety factors in traditional design. Now, if you somehow could reduce this uncertainty, then actually as what you may see, what if we got from this black curve to the black curve with dashed lines, this could also mean that you're more confident in your models, in your predictions. And because you're more confident, you actually know that you have sufficient reliability, even if you can allow yourself to have less materials. And this is really the one of the assumptions that we want to test, and also we want to demonstrate. Can you enable the entire process that leads to verifying this and actually achieving this material reduction? So this is, I would say, a larger part of the project activities is focusing here on this. And then this leads us to actually the overall objectives. So as I mentioned, it's really about these reductions in risk and uncertainty, and we hope that this could lead to 9% reduction. That was like the estimate before we started three and a half years ago. You will see later today whether we achieved that. I'll keep this information a little bit secret for a few more minutes. Well, we start with environmental conditions. As I mentioned, this is like looking at those to achieve some uncertainty, understanding and reduction in environmental conditions. Load assessment. Second part, again, similar objective. Then we go to reliability computation, where we want to use the information from environmental conditions and loads in order to improve the way we compute this reliability and use this information to change the design. Then we also have, since we have been already looking at this structure and we have more modeling capabilities, we also have objectives about trying to optimize costs through, for example, improving the reliability and changing the the way the maintenance is made. For example, if you can predict the reliability of components, then you may want to change the maintenance. And then also, in order to do that, you also need to have models for degradation of components, and that was also one of the objectives we had. And finally, it's of course nice to have all this exercise of trying to or claiming to improve models in different ways. But I think it's also very important to verify what we have achieved overall. And this is actually the last objectives, which actually is doing cost modeling in order to verify whether all the project activities and potential new science actually really leads to these reductions that we expect. Partners. Now, thanks everyone for being very actively contributing to this project. DTU, that's us. We are coordinating the project. We also have IFP and Energie Nouvelle from France, EDF also from France and the UK. So there's actually a couple of offices involved. ETH Zurich, so our Swiss university partners. DNV from Norway, EPRI, the Electric Power Research Institute, that are actually based here in Ireland, in Dublin. That's also nice. We have local local support. And then we have the University of Bergen in Norway. And I also want to say that it's behind all these partners, there's actually a lot of people. It's been, I think, at least 50 named persons have been part of this project, and it has really been a teamwork. I think this is really everyone has been working very strongly to contribute, and it's in that sense it has been a great experience to be part of this project, and that's also one quick thanks to all partners for that. Okay, now click. Can you click that? Yeah. Something happened.
Now you're opening it. Okay.
This is uncertain.
What's up? Yeah.
I don't know. You're an open another.
Can we just click on here once? Yeah, okay, I think we're there.
Yes. Well, sorry for this short interruption. Unfortunately, not long enough to get more coffee, but let's just go ahead. Also, one reason that I think this was so nice teamwork is that we had also partners that were very capable in many topics, and we had both nice complementarities and synergies, especially on these very important topics like uncertainty quantification, which was, of course, relevant for the entire project. Then we have also, as part of the project, in order to look at some realistic studies, we had these use cases. One was a real wind farm off the coast of England, called Teesside. It has 27 turbines, and it's relatively shallow water, but offshore. And it's about 10 years old, and it's owned partially by our partners in EDF. So we had some nice data from the wind farm. Then we had South Brittany, that's a floating wind farm, and we wanted to do floating, and there's no existing wind farms of this size, so we had a virtual case with real wind conditions off the coast of the French Atlantic coast, and with this semi-submersible floating platform on a 15 megawatt turbine, a 15 megawatt turbine placed on the platform. Oh, that's the case. Yeah. Maybe the Teams is doing something. All right. Yeah. So project had 6 work packages. Starting with the first one, so these 6 technical work packages, and the first one was really on data acquisition and study case definition, and that's actually an important one. We really enjoyed, or it was really useful in the later stages of the project. That, for example, we did verify against each other all our models. We had these aeroelastic models. So there was 3 partners that had aeroelastic tools, and we made a study that showed, or we managed to get them to show the same results. So later you can have much better confidence when you compare your actual results. Then the work package 2 was environmental conditions modeling. This was about going multi-scale flow modeling from atmospheric scale, mesoscale down to the wind farm scale, and also also looking at the data for the environmental conditions in order to get results in terms of inputs to other work packages. So like what's the wind speed, what's the wind condition distributions. Then we had used this information in work package 3, where we did the loads modeling on wind turbine and wind farm scale, meaning that you go and look at the wind farm flow level, like wakes, and then go into wind turbine loads. Then, having the environmental conditions and the loads, you go in work package 4, which was live assessment of wind turbine structures. So that was on the main support structures like monopile, tower, and then you're trying to look at the reliability of these structures. And then work package 5 was on component level. So that was for the replaceable components like drivetrains, bearings, but also electrical components, where we did some different simulation of different scenarios and tried to do degradation models and reliability models of replaceable components. And finally, work package 6 combined all this into first doing some optimizations on operation and maintenance based on inputs from work package 5, and then also cost assessment and impact assessment in order to find, again, to combine all the results from the other work packages and find out if we really achieve a good, let's say, the expected impact. So yeah, it's been 3.5 years. That's actually about, until now, that's been almost like 10 people working full time for 3 years on the project. That's I think the total number of hours that people have spent on this project. And our computers have spent even more time. This I can tell you. It's because when we talk about uncertainty and about reliability assessment, this is really computation expensive. Also the flow models, of course. So there's been a lot of computations. Then we have, of course, had many deliverables and reports and publications. So where are we after these? Let's say this amount of efforts. That's a very quick summary. I would say we start with the cost reduction. I think we have actually got up to 20% reduction in the material use based on the case studies based on the T site, so on the existing wind farm case study, which could lead to, I would say, 5 to 10%, or I'll say our friends from doing the cost modeling would say 5 to 10% reduction in levelized cost of energy. Overall, I think that's so we seem to get some very interesting results. And then on the way, we've created some, I would say, very nice advanced new science in terms of new methodologies, new tools, which you will see in the next minutes. So I will now go in a bit more details in some of these technical elements. First is the problem of design and uncertainty. I explained that it's maybe a bit challenging, but and that you need to do it, but I'll try to dive a little bit deeper into it. And the thing okay, now it's going again. Yeah, we need, what are the challenges in probabilistic design? Sorry?
Next time.
Yeah, okay, thanks. So, the first thing about probabilistic design is that suddenly, you need to go from maybe simpler assumptions, like saying we have one, let's say, deterministic value, and then you add a safety factor, which is based on assumptions of the error assumptions. Now, suddenly, you need to actually define the entire probabilistic problem. What are the variables? How are they distributed? How do you put the model chain together? So that's really an additional, let's say, additional formulation problem that you need to define. And that's of course an extra effort. Then we deal with distributions and not only with single values. That adds another complexity in terms of, as I mentioned, the computational effort, because suddenly you need to, characterizing the distribution requires more sampling or more calculations rather than just having a single value. Third one, what if we have, when we talk about reliability, we also talk sometimes about rare events. What are the events that lead to failure? And these rare events, characterizing them also means that you properly, or let's say, simulating them or calculating them in a confident way also needs additional efforts, and also potentially may lead to some simplifications, which may add some additional uncertainty. So overall, some of the efforts in the project was really trying to tackle these problems. And how do we do it? We start with the problem definition, where we try to establish these limit states of the modeling chain. Then we want to go for quantifying the uncertainties and say, okay, we have these different models that we need to use. Maybe there's alternatives, maybe for a specific part of the design procedure, you may have different model alternatives. You may want to quantify the uncertainties of different models and choose the ones that are best. So you make your choices. Once you reach to a stage where you know how to model the entire process, then you still may need to make simplifications, because then if you want to do reliability assessment or computation of probabilities of failure, it takes again more computational effort. Then you want to do simplifications in terms of maybe reducing the number of variables by eliminating those that don't really matter, going for advanced sampling techniques so you quicker converge to your result, and then also finally use these surrogate models, which could give you so maybe replace some more computationally expensive models. So finally, once you have this reliability assessment in place, you want to data design, or at least check if the design is adequate. So that's also like the last step. What are the uncertainties that we actually looked at on the model chain? We start with the inputs, the stochastic inputs, that's the environmental conditions models. We look at the atmospheric conditions, that's wind, turbulence, shear, transients. Then the marine conditions is the waves, basically the wave statistics, and the soil for the thick spot, which was, of course, also, I think, a significant uncertainty. Then, using these inputs, you start trying to compute design loads. For those you need, again, the climate and wind model taken from these environmental conditions, and then you also need the wakes. And then for your load assessment tools, you want to look at aerodynamics, at least in hydrodynamics, and also if there's any structural uncertainties. So all this is, trying to look at what are the uncertainties in these models. Then, in order to make the so-called reliability assessment, you need to also have the strength of your structure. So you need to have the distribution of the loads and the distribution of the strength, and you see how likely it is that they overlap, or that the loads actually are let's say, higher than the strength. And so we also need to have some stochastic inputs in terms of the material or the structural strength. You may notice they're less than there's less inputs or less focus on the materials rather than the loads. And this was a deliberate choice in our project, because you can't really do everything at once, and we wanted to limit the scope to something manageable. And what we thought is manageable is focusing mostly on the loads and the environmental conditions. Now let's go into the specific uncertainty quantification, and also how did we change the model chain? We did some improvements along the way, or at least we hope so. Starting with the flow modeling, this was something done mostly by University of Bergen. Fortunately, Mustafa couldn't be here today, but we'll see a video from him later. So that's multi-scale flow modeling, going from the atmospheric scale down to even down to the structural model, or to the aeroelastic response of turbines, also including some data simulation along the way. And I'm sorry we don't have the time to go in multiple details, but we can always, I think, read our reports and contact us. I think there's something happening there again.
Yeah.
Oh, thanks. So this is just an example. Let's see if it goes. Can you click on the video? This one, the red. Well, that's just an example, I think, of a specific event where we have a nice video of how this simulation goes. And then this event, you go actually through the atmosphere, then you go zoom in into the wind farm level, then you solve the wakes. I think that's so that's part of this work package 2 that we had. And then another part, which may look more trivial, or at least it's definitely less computationally expensive, but it's definitely apparently not so trivial as we thought. It's just getting the joint distribution of variables from data. So as you see, we got some distributions by looking at data fitting distributions. But what was very interesting is, for example, this graph shows 10 different distribution fits, or maybe even more, almost 10. So they are different, right? And this is the same data. It's just that there's a deliberate choice. Which distribution do I want to fit? And then you fit it and you get different results. So that was also a bit of an eye-opener that it shows, well, sometimes, subjective choices actually do have also do come with an uncertainty. So it's not only if even, yeah, despite the data being limited or not, also it's, let's say, some specific choices we need to also take into account that this is uncertain. And I think that was also one interesting result we kept in mind later in the project. Yeah. Then another thing we did was also looking at not only at the 10-minute statistics, but at transient events, which was like going for if there's gusts, or direction changes or frontal passages in the data. And this was work done by DTU that developed a procedure to detect these events in data, then also to incorporate them into turbulence boxes for load simulations and do load simulations. So you could directly simulate measured transient events. And in addition to that, we also did some, this is some kind of probability models that actually tell us what is this one, it tells us what is the likelihood of having an event of a certain magnitude as function of its probability. So in that sense, we also use this information to suggest some synthetic events, something like those are there that could be used, for example, in future designs. Then we move into the loads. And in order to do, for example, load assessment in a wind farm, it's actually good to look at wakes also. And then what could be also very useful is to have a so-called wake parameterization, which means that you can describe the wake situation or the wake interactions in a wind farm with just a few variables. Then you can use this information to train surrogate models. So basically models can quickly predict loads. And this you need because, for example, in wakes, you have engineering wake models that can give you the deficit, but for the loads calculations, you normally need these aeroelastic tools. And so in order to be able, for example, to use these surrogate models, which are called computationally efficient on an arbitrary wind farm layout, a good idea to make this wake parameterization so that you can have only a few variables that describe any wind farm layout. So this is both IFPEN and DTU did some parameterizations. And I think, as you may see here, it really allows us to look at surrogate models that can predict loads. And that is just an example of how it can be used later. For example, this is a virtual load monitor, or basically a tool or a script that can ingest SCADA data, then use this approach of this wake parameterization together with a load assessment model based on simulations that then you have a surrogate model trained on these simulations. And then once you get the SCADA data to give you what are the wind conditions, what is the operating status of wind turbines, you can recover or an estimate of what is the operating history, or what is the load accumulation history, or fatigue accumulation history, sorry, if each wind turbine. Wake models further. We also looked at the certainty. Of course, we have the wake models, but we also want to check if they are really good. And then there's different fidelities going from LES as highest fidelity, large eddy simulations, medium fidelity like the dynamic wake boundary model, and then low fidelity like the engineering wake models. Overall, the conclusion was that with all model levels perform really well when you are looking at deficits and when you're looking at single wind turbine deficit. When you look at wake interactions like this wake superposition, then some models like the dynamic wake boundary model that was not so clear. I think the results were not as good, so the uncertainty was higher. So that was interesting again. And then also this also wake simulations, also in higher fidelity wake simulations were also used together with dynamic modeling of floating wind turbines to find out what is the effect of floater motion on wind farm power production. And there was two effects that were kind of balancing each other out. When you get the rotor tilt, of course, you get the lower any energy production, but on the other hand, you get slightly higher energy production because when you get the rotor tilt, the wake is deflected. Other uncertainties could be into the aeroelastic tools. So blade element momentum method, for example. This is actually a fairly simple model that has always been used in wind turbine design. And our partners from IFPN here were checking these results and against the Vortex, which is a more higher fidelity tool. And we really, I think actually, despite being so simple, the blade element momentum method seemed to be really doing quite well, especially for the T side, for the smaller wind turbine case. Other thing, also drag coefficient uncertainty. I think that was CDF mostly working on.
And
IFPN. So yeah, so that was CFD simulations. I think here maybe the main thing was Morrison simplified model doesn't seem to always be as accurate as we would hope for. So this, especially this drag coefficient. Then also in terms of making it easier to design floating wind turbines, we did a design evaluation framework, which is basically a Python-based framework to, if you have a certain design, you parameterize the floater design in a few variables, like mainly the dimensions of the floater, and then if you input these a few variables, then you have a set of tools that automatically generate the design description that can be used to evaluate it with generates automatically the model inputs so that you can run frequency domain and time domain analysis and evaluate its the adequacy of the design. So for example, we were using it to evaluate the so-called serviceability limit states, which was looking at how big floater motion should be allowed, and then how big pitch and how much is the blade tower clearance and blade water clearance, and just also to establish what are the allowable limits of motion of the floater. Now, yeah, we've been doing a lot of modeling and looking at modeling chain, and now let's try to look a bit at reliability analysis. So using these models to try to estimate probabilities of failure. As I mentioned, this also means that we need to look at maybe some simplifications like this advanced surrogate modeling, and then also some very more efficient sampling techniques. First one, interesting surrogate model where our colleagues from ETH were mainly doing it, is to doing so-called dynamic. So actually making model that can output simulated time series using input, in this case, a turbulence box, and then just directly try to output time series, which is like replacing, in a sense, replacing the load simulation tools with a very simplified version of a very much more efficient simulator. So it's called, in this case, it's called nonlinear autoregressive model with exogenous inputs, and it's on a manifold, so it's MNUX. And there's, I think, on the way, there is also, it's sequentially constructed because you need to have this big turbulence box first. You go through a dimensionality reduction step. And I think maybe it's most fun to actually see how it goes. So, yeah, you see, you rotate, the turbine rotates, and you may see there's two sets of blades. One is the one from the real simulator, or let's say the more high fidelity simulator, an aeroelastic tool, and then this surrogate model, as you see that it actually follows quite well, and it provides a very, I would say, very good estimate of how the overall loads should look, and then you can use this type of simulator in many more simulations. Then we also looked at the Gaussian process as a tool. So sometimes you may want to train these surrogate models in order to replace some more higher fidelity tools. But then if you want to look at rare events, you may also want to consider finding a probability distribution. And if you want to also know the model accuracy, the Gaussian model is very nice because it also automatically comes with an estimate of how accurate is the model where it's fitted. And so if you do, for example, if you want to predict the distribution of a variable in very much in its tail or somewhere in very far area, then maybe what you can do is train several Gaussian processes on each of the distribution parameters of this variable, and then do it sequentially a few times so that you know each time when you train the first process, you see where the uncertainty is highest, and then add some points, enrich your design and do it in this way. So this was used to actually do this ULSO, ultimate limit state reliability assessment. And this was a technique mainly developed by people from BNV. And there was also another technique from that IFBN attempted, which was going for this so-called outcrossing approach, which is again a way to. The idea was again to find where it's most likely that the loading or the outcross or where the reliability will be lowest, or where it's most likely to get these failure events. So in this case, I think in general it's a very interesting approach and also potentially very efficient. In this case, I think we went in favor of the other approach, the Gaussian process one, because in this case we seem to have a few different, like a disjoint set, which was a bit difficult to handle. Finally, but anyway, we did the reliability assessment for the T-side case, the existing offshore wind farm for ultimate limit state, and then what actually turned out is that this reliability is fairly high, so it means that we actually did have a lot of spare capacity. So this if Ben did some further simulations, and it turned out that if we actually reduce the tower thickness and the monopile thickness by up to 20%, I think maybe, yeah, it says around 20%, we actually could still have a very reliable structure. Both actually, in the end, we managed to reduce the mass of this tower and monopile assembly by 20%, and even we didn't hit the stress limits or the buckling limits. It was not just, of course, it's a limit, but the actual limit was the resonance or the frequency criteria, because then you start hitting this the same tower frequency as the rotational frequency of the turbine. So yeah, that's actually a nice result, right? So we had some mass reduction. But then we also had other limit states, and we wanted to check. It's not only ultimate limit state. We want to check also if the turbine can survive the fatigue limit state, and this was the job of mostly our colleagues from EDF. And there, I think for the fatigue limit state, the most challenging part is that we need to make cumulative damage computation. So while the reliability analysis in itself is an iterative process, each iteration needs to actually accumulate again a multiple estimation that covers the entire lifetime of the turbine. And so that is computationally demanding, and because of that, we needed to use some efficient sampling techniques. The one we really focused on is called kernel herding. There's also a Python package now available about it. And then, in the end, there was also some analysis called reliability robustness analysis, which attempts to find, okay, not only what is the reliability of a structure, but how is it affected by, or how important are all the factors that go into the reliability analysis. And it seemed that in this case, some of the material properties was the most important. But overall, the end result from the reliability assessment of the fatigue limit state was that actually the ultimate limit state was more critical. So that's why we overall based this material reduction and design improvement study onto the ultimate limit state. Yeah, so I think that's probably the last technical part. I hope you're still with us. It's about now looking at this component degradation modeling, and then also looking all these results. Can we do some optimization and cost modeling to also an impact assessment? So first on the component reliability, this was something that we both looked at drivetrain components and also electrical components. So April looked at electrical components and BTU at drivetrain components. And one thing we did is for the main bearing, we did a model, a reference bearing model, degradation model based on publicly available data, so that we can publicly share results from it. And we tried to make a material degradation model or bearing lifetime model, which uses shaft loads as input and provides the lifetime as expected lifetime as an output. And this is an outcome of how the model performs on the T-side wind farm. You can see here how, I think you may actually see that the lifetime, how it is affected by mean wind speed and by average turbulence at the site. But okay, so that's also one thing. When you have measured data, that's always what you get, right? This turbine has 20% longer lifetime than the other turbines, and I think that's maybe because there's some data issue that we actually still haven't exactly found what it is, despite of looking quite deeply into it. Yeah. Then, but these reliability models, apart from just telling you what's the lifetime, this you can use to then try to optimize your O&M activities. Because if you can estimate what is the reliability, how many failures per year you can observe, you can try to use this information to plan your operation maintenance activities better. So that's what EDF did in this O&M optimization step, and I think then. I think what we ended up is, I don't think we have it here, but if you can see that, for example, the number of mainly the vessel costs actually were down by more than 10% if you can do this type of optimization. And then, as you can see, this actually reduces the OPEX by about 5%. And this is now actually the overall cost reduction where it comes from. This was EPRI that did a lot of this work, and we look at the CAPEX, the capital expenditure. This comes mainly from the reduction in the mass into the structural components, and then also the OPEX, the operating expenditures. They reduced mainly by let's say avoiding some costly replacements of some components in this O&M optimization. And I think mainly the main impact is actually the vessel cost, the main cost driver. So if you can spare some vessel trips, that actually makes a big difference. So the overall cost reduction is between 5 and 10%. And I'll go a little bit deeper into that in a second, which is like, now let's try to summarize and see what other perspectives. Oh,
Yeah.
I don't know if these slides are somehow different than other slides. They make a difference.
Here we are.
Oh, thanks. Yeah. So we have this impact of 5 to 10%. And I can just show you two figures here. This is actually what the impact would have been from, let's say, 185 to 175. So maybe less, maybe that's a few percent. That's maybe 5%. And this is if the cost of capital was like it was when the wind farm was being built, when the cost of capital was high. This is what is nowadays. Nowadays, we have lower cost of capital. And in this lower cost of capital conditions, we get up to 10% ratio reduction from the CAPEX and OPEX reductions that we get. That's okay, both interesting, but also a little bit discouraging. Oh, we do all this and then all this work, and then in the end, the capital really is the one that also gives really a huge impact. But overall, I think that's also some confirmation. Always, I think we always have known that the financial conditions really are important. But nevertheless, under the current conditions, we expect to have around 10% reduction in the levelized cost of energy. Yeah. So, and also the biggest was this optimization of maintenance strategy due to the vessel cost. But yeah, also maybe it depends also on the technology choices. Like turbine ratings. I mean, if you have bigger turbines, then maybe it's different. Now we have quite many small turbines in this wind farm. This is also another thing just to mention that, okay, this is actually a wind farm which is more than 10 years old. We certainly hope that the community until now have also maybe managed to get some of these already cost improvements. But if not, then at least that's a clear, we know at least where some of the best potential lies. Then also there's a few other things as an impact from the project or how we want to follow up with. One is these standards. For example, I think these gas definitions, which are some of these synthetic gas definitions. I think that's something we would like to introduce in or to hope to in the future standards. And one of the potential standards is this 61400-9, which right now it's called technical specification, which is on probabilistic design. So I think yesterday we heard at the conference, someone was asking, what do we do? Is there a standard on this probabilistic design? And there is actually at least a technical specification. But I would say it complements these project results because this technical specification is very formal. And then here you see maybe, I think I hope you've seen a few practical details of how we can do some of these activities. So to conclude, we start with, I hope you are convinced that we've shown you some examples of how we can look to design at the design under uncertainty. But also along the way, I think we saw some, pieces of science, which each of them is worth something by itself, like different wake models or different uncertainty quantification tools. So, yeah, also we see that understanding uncertainties will lead to design improvements. That's what we think. But also one more, I think, important note is to make sure that I'm actually not, I wouldn't claim that the entire, for example, mass reduction you see into this design is only due to using probabilistic versus deterministic design. I think part of the story is that we had access, or we had considered everything together. So we had the entire design process integrated in one organization, or at least like in one team. And then I think that may have not been the case in these previous wind farms. And this also, I think, has led to some losses of efficiency by also the way you communicate information. And then I think that's also an important learning. And I would recommend all designers that, the tower versus, OEMs, so the developers versus OEMs, to really try to integrate their process more. I think that there's value in that. And finally, we did achieve some, at least what we expected as LCU reduction, which is great. And what still needs to be done? There's a few things, and probably many more. I hope maybe you can tell us. But first, I think, we need to understand also uncertainties in material properties, because we saw that although we didn't focus on those, they can also have a big impact. Finally, this reliability-based design optimization is also very challenging. Still, it needs even further efficiency improvements, because it adds even yet another kind of complexity level if you want to do this full-scale optimization. So finally, I think we also want to make sure that it's not only us that walk away with these results, but all the community can use them. And that's why also we want to reach out, we want to have tools, but also any other ways to get more traction of these, all the outcomes that would be very useful as further steps. So I think that's let's say the first presentation. I hope you enjoyed it, and I think now we may check if maybe there's a couple of minutes. Sorry. So the software. Tools. Just to mention, of course, some of the outcomes that we have to have that are maybe most useful for others is also to have software tools. So University of Bergen, they have done a lot of work on this couple flow modeling. I think one of the tools is called SEDOS, and you may also want to check all the publications. Then there is another tool called Hypersim, which is doing turbulence generation. That's maintained by DTU. So that's like efficient turbulence generation, including constraints, so you can add some measured data points in it. Also non-Gaussian turbulence. And this is in Python. And then we have this perspective to put together this cross modeling tool. I don't know if that's already ready or soon will be. So, but it's just to use again all this information to. I think that's also useful to have a more open cross modeling tool also in Python. Now I think now we're ready. I think we should be out of slides. Yeah, more information will be on the website, and the website should be used as link to further resources in the future. And now let's go and check if anyone has already asked any questions. I think now let's use a few more, just a couple of minutes. I can see there's a couple of questions, and then we will anyway move to other parts of the presentation, and then we can have more open discussion. But maybe that's just one question that we can check. Can you speak about more about the use of GPs? Were they trained on observed data or simulated data? I can maybe take. I don't know if anyone wants to elaborate, but yeah,
maybe I can try. we used GPs in different aspects of the project. First use was in order to compare some simulation tools of different fidelity. Typically, as you mentioned, Nikolai, when we wanted to estimate the model uncertainty, the idea was to compare some design of experiments that were relatively dense in terms of parameter space for the engineering tools, and to try to define the gap between them and the high fidelity tools, typically between engineering weight models and AES, for instance. And the interpolation is done, of course, by Gaussian process, which provides the benefit to quantify not only the mean, but also the uncertainty in the whole space. So this was the first way and first usage of the Gaussian process, I guess. Second one is on the reliability, typically design, in particular, that were used in work package 4, and in which the idea was to use the Gaussian process in order to make some simulation on some points of what we call long-term, parameter on mean wind speed and turbulence. Then you need to make short-term, multiple replications in order to have a sampling of the short-term area. And then you are using some fitting of, I don't know, it was Gumbel fitting for the maxima. And you are using Gaussian process in that case in order to extrapolate these results that is conditional to some long-term properties in the whole long-term space in order to have the global, I would say, failure probability of your structure. So this was a second case, but I think the question was it on simulated? Yeah, definitely it was more on simulated. And the fact is that we were supposed to work on observed data, but actually it's the very final task of the project that is still ongoing at the moment, taking benefit of the fact that EDF was provided some, I will say, strain gauges and with high frequency, so data that could be exploited in order to see how could we constrain the predictions that we are making with the confrontation of our models to the modeling. But actually, it was very starting recently. So I don't know, Nikolai, if you want to complete.
Well, that's fine, thanks.
That's very good.
I'm sorry, I always want to touch, so
Can we see if there's any other? I think there's a couple of actually good questions. Down. Oh,
No.
okay. I think there's.
Right here is one for
Oh, there you
one
go.
out of four.
I think if you press this little down arrow.
Or
This
enter.
one.
Top 3 factors impacting LCOE. Let's do that very quickly. I think that's come on.
Yeah, sure. So I'm like, as Nicolas mentioned, sadly, the biggest factor is the cost of capital. So we just did the exercise. The wind farm was built in 2012. So it's in the UK. So based from the data, we saw like weighted average cost of capital 12%. If we take the 6% that are more today, it's almost half the LCOE. So, but if we are focusing more on the technical aspect, there is the failure probabilities. So like the more your components are going to fail, the more you will need to send the vessel, because for offshore turbines, the vessel cost that drives the entire LCOE almost. And then like also the design of the wind farm. So for a given wind farm capacity, like the bigger is the rating, the less turbine you need to install. So the less maintenance activity you need to perform. And for a given AEP, you reach a lower OPEX. So that's we've kind of run that sensitivity analysis, but that's reasoning with a constant failure rate. So if you think about installing a turbine which is twice as big as the current model, you need to think like, is my blade going to stay with the same failure rate, or is it going to double? And in that case, you're going to lose the benefit of the going to bigger turbines and reducing the number of maintenance. Yeah, it's really on the OPEX side that we saw like the biggest influence, and that's also why we say OPEX can be reduced from 2 to 10%, just depending on the assumptions that you consider.
Let's see. Yeah, so.
That was
I think that was just I suggest we. Okay, I think that's, yeah, okay, now that's, I think we already answered that. I suggest we now, because we have a few, because each partner had a small statement to make, and then we can go back to the overall final session. So let's see if we go back to our presentation. So let's start just, I think that's about 10 minutes of us, each partner saying a few words, because I've been talking a lot, and now let's go. And now actually I still talk for a minute or two, because Estelle, I think if you could help me with the next slide. Yeah, so what did you learn from this? And just wanted to show that, again, we have a team of more than 10 people, 13 people that have been part of project in different times. We've had a lot of new tools and capabilities. First is all the surrogate modeling. We did new things, especially on the wake parameterization, which we also had as a means to develop this remaining useful life procedure. Also, these transient events, that was very interesting, because then I think that opens up for new standard definitions, and this is something we also very much are interested, because it has a significant impact. The floating wind turbine, we learned better how to do floating wind turbine design. And then we had these component degradation tools that also is it's also a new important topic for us. Finally, what we also just learned as knowledge rather than just tools, that is basically the better understanding of probabilistic design, certainties. Also, we had, because we managed to try our own tool chain on quite a few things. Now we have some uncertainty assessment of some of these elements, and then also figured out some oopsies. Some places are more uncertain than others. And again, this suggestion of updates to standards is also kind of learning for us. And also using the chance to thank the entire team in the queue. And next is IFP, EM.
Yeah, so I try to take the relay to your impressive talk. Thanks, Nikolai. There is a kind of emotion for me, because actually the project started 4 years ago. I'm thinking about the proposal scope elaboration during COVID lockdown in France. So it's a kind of special memories for me in particular. Anyway, so you have a view of the teams from IFP Energy well that was involved during all these years in this project. That is was a lot of satisfaction for us to participate, both for the results and also because we appreciate a lot about the consortium and I will say the quality of collaboration with partners. Some of them we already knew, like EDF, but all the others we discovered during the project, and it was really a great result for us to discover this team spirit of Hiperwind. So I wish to everybody that involved in a project like this to experiment something like this. Anyway, coming back to the key lessons for IFPN, I would say that yes, we were concerned mostly at the beginning with evaluation of model uncertainty for both wind farm wake analysis and also aeroservo hydroelastic, so both aerodynamic loading and hydrodynamic loading. And so we observed the like others, of course, but comparing with AES, that we have limitations of engineering wake models, typically with the role of atmospheric stability. And as Nicolas said before, something needs to be checked again for the wake superposition, even for tools that are already largely used. So this is important to know and to go on it. We confirm the differences between for the aerodynamics that was expected at the beginning, but we confirm this systematically. And then we experienced also with EDF that we need to be careful for floating, because fitting of hydrodynamic coefficients is a difficult task. And when you do it from CFD, you can introduce very large uncertainty in the hydrodynamic behavior of your structure. Finally, what I mentioned here, also we've seen a presentation today again of, I don't remember, I guess it was DNV, on this topic. So we can see that coupling of floater motion is important because you have a compensation of stuff. So this is important to make evaluation of the wake analysis to take into account this kind of stuff. And then we modernized, I would say, the model chain that we used at IFPDN with fatigue, with this parametrization. And we demonstrated it actually in a project that took place in the meanwhile. A good comparison with observed data, so it was very successful for us. Just to work actually on utility state. So I work mainly on the. Yes, I know.
So in this project, I work mainly on the estimation of the failure probability. So we knew that to estimate this kind of probability, you need many simulations. And so the first takeaway was that now we have efficient method to compute this kind of probability. And the second takeaway is that this method not only are efficient to compute failure probabilities, but you can also use this result to reduce significantly the mass of the wind turbine.
Then we have EDF, and we have both Emmanuel and it's one here. And I always want to.
Okay, I will talk first. I think as well, yeah. Basically, I joined the EDF, but before I joined the EDF, I worked in DTU, so equally put my name also there. So it's like, so I know both academia and the operator now. And at the EDF, many colleagues are involved in the Hiperwind project. And we can see a few names. It's not a full list. We have Anais, Christopher, Sandre, Emmanuel, and Subang and me, and Nasib, Elias, Pia. And you can contact us if you want to reach us for for some perspective or collaboration. So we have some key learnings. The first one is we increase the robustness of DIGO. DIGO is the EDF's turbine simulation tool, similar to HOG2 OpenFast. So we also have a better assessment of wave field and have a better quantification of the margin during design. So it may reduce some unnecessary conservatism, but it also means we need to apply this kind of probability-based design methodology. So it's still on the way, and my colleague Emmanuel may comment on that. And then for the operational stage, the above is for the design stage we can apply, and then for the operational stage, we worked with the DTU to apply this component reliability modeling for the main bearing lifetime estimation and mapping. So you can see which bearing is worse during for the other turbines in the wind farm. And also we developed an advanced O&M optimization tool. So you can perform a short-term optimization, like 1 year, like for the coming year, but you can also perform a long-term optimization. It's like through the lifetime, maybe you can combine the future failure or replacement in 1 year. Sometimes you get a larger reduction. Yeah, the vessel company usually give you a much larger discount if you can combine some. And this tool can allow us to reduce the maintenance cost and also the revenue loss. And we need to share these results with our asset management team. Like we have several offshore wind farms to get their feedback how they can use this reliability modeling and this optimization tool in their daily work. And for EDF or R&D, we have a lot of in-house tools and like DIGO, also foundation design, O&M modeling, and cost modeling. Some results has been implemented, some may be integrated in future. Yes, thank you.
Thank you, Subang. I would first thank all the partners of the Hyperwind project, because in fact for us at the R&D division of EDF, we were almost beginners in the field of wind turbine. I'm speaking on the side of uncertainties. It was the first experience in terms of uncertainty in wind turbine, and also the first experience in European project in this area. And I felt that all partners were very patient with me. And it was a very fruitful collaboration. So I'm more focused, of course, on the contribution that I supervised that is about fatigue reliability assessment. The main contributor is not here. The main contributor is Elias. His photo is here. And Nikolai mentioned this task in his technical review. So our main learnings regarding this task are that we had to, it's the calculation of the mean global damage is computationally demanding. And for that, especially in the term of reliability, in the context of reliability assessment, of course. And for that, we had to develop a specific sampling method, given data sampling method that uses the possibility of using parallel computing. And thanks to this, it was an attempt to reduce the calculation cost. And the reliability study and robustness study showed that we remained with, on the T-side use case, we remained with low probabilities, much lower than the standards. But these probabilities are very sensitive to some variables, and especially some some material variable, that is the critical damage. So as Nikolai mentioned, maybe in the following it would be good to investigate uncertainties on structural and material properties. Another learning of this reliability task was that the no-wake effect that we identified on this wind farm of T-side. Thanks to you.
That's me. Well, I present the chair of risk safety and uncertainty quantification in ETH Zurich. So we're kind of the academic partners, or among the academic partners here. So our experience is a bit different because we focus on methodological research and uncertainty quantification as basically a probabilistic tool. So we're not really attached to any particular application. And here's the team, of course, is Bruno Sodre, who is the professor, the head of the group. There's me, I'm the senior scientist in the group, and Stephen, who was the PhD student who actually basically ran his own entire PhD under the auspices of this project itself. And what was interesting for us is that through Hiperwind, we got to know a completely new community to us, at least, which is the wind turbine modeling and design community. And I would say I second the sentiments from both Martin and Emmanuel that I guess the main, let's say, learning for us and takeaway for us is the network. Basically, is getting to know a completely different community and getting to know all of these kind of interactions that you can have with them, with you guys, potentially. And we focus on non-intrusive methods, which means that all of our methodologies are developed to solve a class of problems, not a wind turbine problem, but a class of problems. So what we learned, which was through this deliverable 4.1, we learned actually how to solve or surrogate, if you want, data-driven surrogate models for dynamic moving in time series out type of problems, which is a rather unique research avenue, which opened a completely new set of basically publications and research and so on and so forth. And what is really fun is that this is a class of models, as I told you, and of course we used it within the project, but now we are using it also with application to completely different body of problems. So I'd say the most correlated, because it contains wind inside, is high-rise buildings under basically wind loading. That's one class of problems. But it's really interesting for us is seismic fragility analysis, because buildings respond essentially to external time-dependent loads, pretty much like wind turbines respond to high-dimensional turbulence boxes. And what is really fun is we also use it for automotive design, as an example, designing suspensions or how stuff respond to irregular roads. So yeah, for us, it was a really fun experience. And if anyone is interested into seeing the more methodological side and maybe probabilistic side of things, so someone who doesn't get bored easily, just drop a line. Thank you.
So can you scale this up and down and so on and utilize for other industries as well?
I would definitely say so. We work similar stuff for, as an example, additive manufacturing, as an example, this kind of thing. So yeah,
All right. So I joined only the project 1 year ago, so I don't have like the 4 years experience Martin mentioned. So maybe I'm not the most legitimate here to talk about Hiperwind, but there's the team here. Then we worked on Deep 5.2 and the grid aspects of those grid events and impact on the component lifetime. I worked mostly on the 6.2, the assessment of the development on LCOE, and then we had Nicolas and Raja who provided guidance and also shaped the proposal at its very beginning. So maybe you should talk in my transition, but I'm going to keep talking. Now, if, the main takeaways for me, and I would just want to echo the comments from Martin and Emmanuel, also Stefano, it's like really the collaborative aspects. Like if we think it's starting from meso scale, large scale simulation, just to get to this very detailed description of the flow field, then adding the weights on top of that, and then including the reliability, predicting the components. All of that is just possible because all those partners were there. It was a successful collaboration, and we get a real reduction of the LCOE by that. So it's a successful project in that sense, and I think the collaborative aspects is definitely one of the biggest enablers for that. Also, just want to highlight, so we presented like the work from a work package 4 just gave us very significant mass reduction of 20%. That provides a substantial reduction on the LCOE, also the optimization. But there are like other parameters I mentioned earlier, like the number of turbines, also like the failure rates, those things that are revolving around, but they were not part of the scope of Hiperwind that have a drastic impact also on the LCOE. So maybe we should keep on that project and investigate those things. So really like trying the influence on those parameters. And yeah, like just as a world, understanding uncertainty, and how they play, and this the entire holistic approach, considering everything is really key if you want to become better in designing the turbines. Yeah, that's it.
Thanks. Now it's video time. That's University of Bergen, and I think we have a video by Mustafa. We also be online.
The project had a broad spectrum of learning for me that ranges from technical to non-technical and soft skills like collaborative learning skills. While, as I mentioned, the project was mainly virtual. My main technical learning from Hyperwind project relate to addressing the objectives of work package 2 and particularly its 3 first tasks, and as well as collaborations with other work packages. The tasks in work package 2 aim to tackle one of the key grand challenges in the offshore wind energy in terms of reducing uncertainty in environmental modeling. This involves gaining a full understanding of the inflow conditions and such as wind and wake flow within and around offshore wind parks, which this influence, on the other hand, the loads, structural responses, and the power productions, and also applied control strategies in the turbine and farm levels. Such kind of learnings, of course, are key for future offshore wind energy development when we have larger wind turbines located further offshore. The project.
Okay, now we have, thanks Mustafa. And now we go to another Norwegian partner from DNV. That's, I think you can just for the sake of Eric, I could explain who are the other colleagues from DNV that were working together with us. So that's also Odin, Christian, Ong, Carla, and Sebastian, and they've been working a lot on ultimately we state these tools for extreme response estimation. So Eric was himself doing a lot of work on the joint distributions, while the others, mostly Christian, Sebastian, also the others worked on these Gaussian process models. I think we also have a video from Eric.
Start.
Hi, my name is Amy Holland, and I'm as a research scientist at DNV. We are very happy to have been part of the Hyperwind project. Together with several of my colleagues, I've had the pleasure of working together with highly skilled researchers from the project partners on challenging and relevant problems related to offshore wind. We have developed and gained experience with generic methods for probabilistic design and structural reliability assessment for offshore wind turbines, including how to account for uncertainties in various parts of the modeling chain. Some of the specific project outcomes that are highly relevant for DNV are computational efficient tools for long-term extreme response estimation and ultimate limit state assessment. Improved tools for wave modeling, including shallow water effects, and probabilistic multivariate models for metocean conditions and uncertainties associated with them. These competences and tools are not only relevant for offshore wind, but could be applied to other marine structures. We will continue to work on these methods and tools to further validate them and possibly include them in our recommended practice and our future services. We believe this to be useful not only for DNV as a company, but to the ocean and offshore engineering community as a whole. We also hope that by being part of this very interesting research project, we have made a small contribution to promote offshore wind as a viable and clean source of energy for the future.
Thanks to everyone. So yeah, now I think this was all the partner statements. It also ended up nicely with the saying about wind energy. So now can we go to? I would like to ask you guys to use your phones and maybe give us a few answers quickly on what do you think? What do you find important for this project? And that also includes if there's anyone online that's interested in joining. So it's just, I guess you can scan the QR code or get the code. And I think if we go to the poll page, we will anyway see the same slide. So please, if you can just log in. I think we can.
You have to. I think it is. It is this one.
Yeah, it just needs to go there in the
It is one.
I think it's not this one because it's not live. Is it live here?
Yeah. Yes.
It's actually. There's some people here, so I need to drag this one off. No, okay.
Yes.
Okay, now we have the live. We have 8 people online. Let's wait to see a few more. If we get a few more. 9. And now I'll get the other remote and try to see when we can get in the.
Doesn't stop.
Really? No, that's 10 people that are.
It is the same person.
Everyone just trying to give thumbs up. Yeah.
Anyway, so for those of you that I think we can start answering, and then anyway, while answering, there's also the code is up there, so one can still go and access the survey. But now we are 13. Let's start. So, what results do you find potentially most useful or interesting to apply in your work? Please try to answer. It's open answers, so you can just write short sentences or a couple of words. And partners are also welcome to write. Sampling methods, okay. Reliability analysis, surrogate models, financial modeling, different things. Yeah, so it's both surrogate models and financial models. Now we get a few more responses. Very nice. Integrated reliability design mindset. I agree. That's also interesting. Yeah. LCOE optimization, certainty models, damage models. Okay, that's almost everything. That's really good. Actually, in a minute, let's wait. You're also welcome to give more than one answer if you think that it's like several things that you find most important. So we can also, is anyone else expecting to do more answers, or are we fine? If we're fine, then I would, we can also.
My battery, so just quick question. How
Yeah.
quickly we can shift this knowledge, this experience to onshore?
That's a good question. Well, I think the modeling chain we had was mainly offshore, so we had really focused on the main uncertainties that could be offshore, which is, for example, we talked about waves and about monopile design and about the specific extreme events that happen offshore. I think if it's onshore, I would expect that we need to rethink what are the main uncertainties that drive the design. That could be, for example, the terrain effects. There's a main difference. Also, maybe weather, also atmospheric stability and turbulence.
Uncertainty problems on onshore, to be honest.
Yeah.
You expect it should take 1 year or something like that?
May I complete? I would say, for what concerns the quantification of model uncertainty, I totally agree with what I said, and in particular for wake analysis, of course. For what concerns reliability methods, the main objective of the project at the beginning was to demonstrate that we can make accessible this kind of computations to leverage the gap between the research academy, to which it was still belonging, and the fact that some people like you are using them.
So you open Pandora box.
Exactly. I mean, this is the methodologies. They are very generic and general, so they definitely can be used with sequential sampling for ULS, and the way the fatigue is also computed by decreasing the maximum possible the number of computations. This kind of stuff can be totally applied directly for onshore cases.
Perfect.
You're welcome.
Okay. So maybe that's actually you already maybe got an entrance to let's say you already gave an answer maybe to one of these. Is like, what are the main activities you would like to see in future research? Apart from applying it to onshore wind, anything else? Dynamic wakes really fun. I can answer that one. I think that there's several groups that are trying to do that. Right?
I know it.
Sorry?
I asked.
Oh. Improvement on tools, graduate on challenges, foundation.
Can I answer the pin? Can I answer the pin, please? So pins are quite an interesting tool that is very popular and popularized lately. But we had access to pins when we decided to develop our own surrogate methodologies. Problem with pins is that they don't necessarily respond very well to, let's say, control systems on one head side. So basically, you have a kind of a dynamic stuff that changes over time. And stability and convergence is not always very clear. They're also very expensive to train. That's another thing. So yes, we investigate them. We try to use them, but we also want to go through completely different strategies because there's quite some hype. Some of it well deserved. Some of it is hype.
Okay.
Could you elaborate on some the left question on how to convince the OEM for following the advices and plans? I don't know if the people who ask the question is online or physical, but I think it could be interesting to elaborate on it.
Yeah, interesting. I used to work for German manufacturers, and usually they were not very attentive when the external findings were up. So they were believing they were smart enough to do their own turbine work. So this is, I mean, obviously there's done a lot of research on how to convince them to listen at least, yeah.
I mean, okay, so once you have some, let's say, reduction of uncertainty on your assets, we're asking what could be the way to communicate with OEM in order to,
Yeah. So what would be, for example, you identify better bearing for make bearing for as the OEM has identified, or you've identified better to say a way to calculate loads in the main shaft. And all those things. My experience is that they are not very attentive.
Nikolai, maybe you would be the best to answer for this.
I would also say, well, one easy way to convince OEMs, at least I see it, is not easy, but of course, like way that it will definitely have to convince them if you have legislation, standardization. So once you have that in place, like standards, then it means that they will simply have to follow. But on the other hand, I think right now I don't see it as a possibility to have a standard which completely replaces the current deterministic standards. I would expect that there is a probabilistic standard which gives you an opportunity. So I'll say then one way to convince OEMs to follow advices and findings in these cases would be just to show, if you actually follow that, you put maybe more effort, but then you actually get the reward of maybe getting a better design, which, then it's better for the business. So in that sense, it's, I think right now it's, the probabilistic design is in a stage where it is an option, not, I wouldn't expect that it's compulsory way of doing it. And then it would be like, the motivation should be that they actually can achieve more. And this is actually the philosophy that has been, I think, for some time also included in the IC design series. For example, in the -1, I think in the latest edition, there's also more, let's say, provisions for doing some site-specific load assessments, and also depending, for example, there is one specific load case of extrapolation, like statistical extrapolation. And statistical extrapolation is also a very difficult exercise because of finding these tail probabilities with very few data points. And then there, for example, there's 3 different levels of complexity you can apply, and the higher level of complexity you apply, the more accurate you get your result, the lower the safety factor you need to apply according to the standard. Then this is like a way to show if you actually put more effort, you may be rewarded with a better outcome. So that's maybe one possibility. And just since I'm still talking, I could also use the chance to say that I can see someone ask what is a PIN, and this is physics-informed neural network.
I answered with a question, but it doesn't show up.
All right, I think
maybe I can try an answer for what concerns the weight modeling for floating. Actually, we recently at IPEN started an activity in a joint industrial project that is called FAME, so FAME, with my colleague Adria Boras-Nadal. So if you're interested in this, you can contact me, and I will put you in contact with Adria, of course. But this is a continuation, of course, of the results that were shown just before with, the interaction between the floater motion and the weight. So still an ongoing activity.
Great. Anything else we want to discuss from this table here?
Maybe we scroll down. I know there is another question.
You can probably see there in a toolbox, yes, that we don't see at least.
Simplifying the process, I guess.
Yeah,
itself. Display.
Yeah, and then you can push back.
Yes.
Find the process with quick early stage design assessment. Okay, that we done.
So I don't know again what was exactly the idea behind this question, but maybe what we could say is that the results we presented, mass production, etc., for the monopile case, actually it was a recent result. But so typically it was going beyond the expectation for us in the results, because we were it was possible to make the design optimization while during all the project we were honoring the question how we will face this design optimization at the end. So actually it was a good surprise for this. Of course, I would say we want to elaborate on this depending on the change of foundation, of course, and when we go to floating, depending if we go to the different floater, you have different motion, and it will change, of course, maybe the main assumption that is behind this is that the conservation of the bending moments when you change the design fitness, etc. So it needs to be checked. If it's still the same, we found that for the semi-submersible, we cannot do this. We must go to something more complex, but that is still possible with some surrogate in the space of design parameter space, something like this. But the question remains, it takes, I don't know, from a TLP foundation for floating, that is less moving, what happens? So these are some things that we would like to investigate, of course.
And also just to complete, for example, we did a lot of work also on this parameterization of the design process, where for this, for example, the semi-submersible, you can get some answers on how suitable is a design by, yes, introducing this, changing the dimensions of the floater, and then try to understand what is the limit state, or what is the reaction of what is the response of the floater to these changes. And yeah, it's just as you said, it's you may be able to have some quick assessments, but if you want to go in more details for some particular limit states, then until now we seem to need to go to time domain simulations, which are of course expensive, and then I think that's actually some work we do intend to do, and to try to facilitate this process, maybe introduce further simplifications or workarounds to be able to have a good design estimation, which does not take all these several hours of compute time that I guess you need to validate design. And then also, I think that's in order also, if you want to have this perspective of doing design optimization, as in the classical sense of this gradient-based optimization or stochastic optimization, but then nevertheless actually trying to find an optimal design in terms of mass reduction or cost reduction, then if you want to do this, you need much faster computations, because right now, if you need to take a day per iteration, that's not very useful. So that's I think still I definitely agree that this is a good topic to continue working on.
Yeah, I'm just wondering, there is a question, I don't know if it's fully displayed, but the use of finite elements in order to improve engineering models. You see what is behind, because I'm not sure too.
Not sure. To me, it could also be like hybrid approach, such as finite element models. How could you hybridize? I mean, one thing that we actually trying to do is do this surrogate modeling, which is in a sense looking at engineering model, a surrogate model as a model which approximates the more advanced models like the finite element models. Actually, we do have the finite element on the beam scale. We have these aeroelastic tools, which are finite element models of beam finite element models, many of them. And in that sense, one thing that we have been doing is supplying these surrogate models. There could be also other possibility, like improving the accuracy of engineering models. Another possibility which we have is also trying to calibrate these models with data. Actually, this is something we intend to work on still. We have actually a few months left in the project, and the remaining deliverable is about learning how to update models. But it's mostly based on data-driven models, which we will be, then you can use this model parameter updating. That's one possibility. And I guess Stefano maybe wants to add to that.
If I can add something, one of the approaches that we've been working on a completely different project still from EU, it's a so-called gray box modeling paradigm, which is kind of more popular or popularized to a degree from digital twins and this type of machinery. Where the idea is basically that you use the finite element model as your starting point. I mean, you calibrate maybe through real data, that's okay, but you always retain some degree of discrepancy with reality. And then you use essentially machine learning based methods to fill in the gap between the prediction of your calibrated model, which is based on physics and knows about the equations, let's say, and actual reality, which seems to be ignorant on the equations that we use. This is a hybrid approach.
Can I ask if there's anyone in the audience that has any thoughts or questions? Because I think my next question will be how to reach out or how to interact further, but maybe before that we can see if there's any other more technical or project related topics we want to discuss. Or if there's anyone online that would like to ask a question, I think that they need to ask in the chat or. No. Okay. There's one there. Yeah.
During these sessions, we talk about like all the different types of model, like high fidelity models, we have engineering models, and then we talk about surrogate models. And when we talk about the design process, like from design till the execution, can you summarize like at what phase, what models will be important? Because each model will have certain advantages and disadvantages. So
yeah, that's a very good point. So let's say how. But I think here I may also need help from others because it's actually a very. Yeah, this question requires a very long answer. So, but let me try. Let me start from saying. Yeah. So on the environmental conditions, we have. It's. I think we need to start from the baseline is this probability distributions of the wind speed, turbulence, and all other conditions. This is an input that you will need to have for all types of situations. And then there is also these very advanced models in terms of coupled flow. I think these are for actually looking at specific events and more looking. I don't think you need to simulate or you would need to simulate the entire lifetime of a wind farm into this complete chain. But that could be for two things. One is simulating some events of interest, like you say, okay, now there is a very special transient event or a pronto passage, and you wanted to see if I would say more also verifying your other models, that whether your more engineering level models, whether they are adequate for this situation, and then these higher fidelity atmospheric tools could be the ones that give you this answer. Also, and actually, it's unfortunately not too much maybe in this project, but there's also currently a lot of research in using these high fidelity atmospheric modeling tools as let's say to build some databases of realistic conditions, because we also know that, for example, our turbulence generation models, they assume some it's a Gaussian random Gaussian field, so they're statistical models rather than pretty physics based. They have some physical background, but it's not it's very simplified. And then because of that, I think that maybe for some situations like a more realistic flow inputs could be relevant for the rest of the modeling chain. And then I think now a tendency, for example, is to make databases from high fidelity simulations where you can take some pieces of this and then use it as inputs directly into load simulations. And these there's also maybe ways of recombining this through taking the some decomposition or some generative machine learning tools. But overall, the idea is to be able to generate flow, let's say, realizations that are physically more correct. So I think that's, let's say, the two applications of these high fidelity flow tools I see. One is to make these realistic flow realizations, and second is to just check for different very specific conditions. And then the statistics on what is the overall, let's say, wind climate and wave for other climates this is most likely based on data and some probability distribution fits. Then we go to the wakes, let's say the wind farm. I would say there, overall, it seems the engineering wake models are good into establishing annual energy production. That's I hope we all agree. And then if you want to go for loads and more to look, I think, for example, if you design a wind farm control system, that this is also a new area of research. We actually right now, as we speak, I'm working on another project with the DTU and other partners where we want to do this integrated wind farm control. And then there you probably need some, if you want to include more objectives than just annual energy production, then you may need to do some higher fidelity wake assessment tools, at least on the dynamic wake meandering scale. But also we saw that
and maybe to complete, as we said before, when you have special events, typically when you are deviation from the neutral stability case, for which the engineering models were calibrated mainly, and also wind turbulence generator you are talking about, like the well-known, you are talking about Hypersim that was developed by DTU, but of course you have Turkcin by NREL that you probably know also. All of them were calibrated and validated in neutral stability conditions. So when you are deviating from this, which could be important even for IEP because you are in the large occurrence part of the Weibull distribution of wind speed, then you need to go to higher fidelity wake simulations in order to quantify the gap because we quantified actually that it's important in that case. So deviation from neutral stability, and also, as you said before, strong superposition case, in which you have these two conditions in which going to higher fidelity for wake simulation is important, I guess. So
no, that's all. And also, when we talk about multi-objectives beyond annual energy production, then it's likely that you need to go to higher fidelity. And then, yeah, what next? After we know the waves and the loads, then we have the aeroelastic load assessment too. And I can see Emmanuel, you wanted to add something?
Yes, because maybe it's a beginner question, but the outcome of our reliability study for fatigue was that weight was not so important for reliability. So maybe it's not too much necessary to investigate weight.
Maybe I can elaborate on this. Just I try to be short. We've got to specify that this sentence is specific to the limit states that we consider in the project to be the most critical one, that is the tower bending at Mudline for this monopile case of the Teesside wind farm, actually. So it's not a general conclusion. And of course, taking just this case study, if you are going to something that is upper, typically for the blade fatigue, this is something totally different with a very large part influence of the wake on this part of components. So when you go to the load analysis, you've got to think about, it's not general, you've got to think about what kind of limit state I want to elaborate. Is it fatigue? Is it ULS? Is it SLS also? And depending on this, depending on the components you are considering on the wind turbine, it will change about the influence of the uncertainty depending on the case. So this is something that is to be maybe we were very fast to the most critical case because the time was limited, and so interesting to have something more general, taking time to consider the whole point of view of the diverse limit states and the condition. So sorry, I hope it clarifies about your conclusion, but
I could just as a last point on this, I can actually mention that in one of the slides, which was far back, I think now it's going to take 5 minutes to find it, but there is on the one where I was showing this remaining useful life assessment, there was estimation of the change of fatigue loads as function of wind direction, which is affected by the wakes because it's for a wind farm in the center of the wind turbine in the center of the wind farm. And you could see that there is actually peaks where for the blade loads, there's peaks where you have strong wakes of the wind turbines. So for blades, for example, the wakes are important because then you also have this half wake situation and basically cyclic variation of loads coming in the water wake. Then you don't get that for the tower is better because if you have a wake, suddenly you have lower wind speed, and then which actually leads to lower thrust force, and then overall this kind of lowers the loads on the tower. But for the blade, because of the cyclic nature of the loads, then you actually do see an increase from wakes. At least that's. Sorry?
You have more dynamic.
Yeah, but the dynamic, but I think also some it's lower overall somehow. So it's like because the thrust, you can see that the let's say the mean force of the tower really follows this thrust curve, which goes up and then down and then slightly down. And then if you just reduce it by 50%, apparently that maybe the effects more or less cancel out. You're right that there's probably more cyclic loads, but on the other hand, you also have 3 blades. So maybe one is going into the wake, other is going out of the wake, and then overall it seems like it's less effect on the tower than on the blades.
The amplitude is the one in the parts that is affected by the
Yeah, exactly.
we can maybe just complete also. So after we have computed all these, let's say, talked about wakes, then we talk about load assessment. And there, to be honest, I don't know if we have an alternative to right now to the aeroelastic simulations. Of course, we have this, for example, this simplified tool that Stefano and his colleagues developed, which I think it's also very useful because this like the dynamic surrogate. But I mean, you still need the aeroelastic simulations to train it. So in that sense, you still need to develop an aeroelastic model to as I think as a step analysis. And then I think that's. I hope that overall this kind of concludes this question. Yeah. Anything else? Anyone?
I want to add to the turbine you mentioned, that one has a higher maintenance cost. I think our colleague also mentioned it has a different water depth. So if you build an offshore wind farm offshore, ideally you may think all the foundation have the same depth in the simulation, but they don't. Some may get more, a longer tall foundation and taller. It's you may get more tower acceleration than others. So you may also can see this effects maybe in a simulation if you want.
All right. Can I ask if anyone thought that something didn't fit? Something said, that's, that sounds weird. Anything like that? What we discussed?
Or even online.
Or even online. Again, is there those no online?
There are a few online questions.
Yeah.
Can you just comment on that mass reduction? 19, you get around 19% reduction in mass during optimization. In the total optimization study, does that kind of imply that the factor of safety that we are going with right now is too high and making structures very costly? I think in some slides I've talked about when you performance optimization. It's foundation or tower mass which reduces by around 19%.
Yeah, I mean, you are telling about where it comes from, the 20%, or where
Just a comment on the factor of safety.
Yes. Okay, not easy to answer. There is part of the answer that is, if we consider the decide case actually, and I hope I don't disturb about the confidentiality, stop me. Anyway, I think as usual, you have this OEM problem, meaning you have, as Nikolai said before, many projects are designed with some parts of the design that is done by the OEM, and with some, I will say, not site-specific, but generic information. Typically, you have this reference wind turbine class that will consider some reference wind speed in the standard of IEC or DNV or others. And then it will introduce some conservatism in the design, of course, because it's not site-specific, but typically generic. Typically, for this side, I think that the work that was done by DNV in order to try to elaborate and establish precisely the joint probability of wind and waves occurrence for this site, it was not available at the time of the design, this kind of information. So, of course, there was a part of the conservatism that was coming from this. That could explain a part of the 20%, of course. For the left part, I will say, yes, it's still, we can conclude anyway that another part, and significant one, was coming from the fact that we were able, because we propagate the uncertainty in the whole chain, from mesoscale to site-specific wind and wave, like I just mentioned, etc., just to the model uncertainty, and then to discriminate between the different limit states, which one was a critical, identifying one, and then for this one, computing efficiently the reliability, etc. We were able to make the design procedure, design optimization, because of these assumptions that was demonstrated that when you reduce the thickness, it does not change the bending moments. And so because of this, we obtain a reduction of 4 order of magnitude, I guess, on the probability, annual probability of failure. And as Nicolas mentioned, the critical condition because we checked in the same time the manufacturability, the buckling, and the tower resonance. And I don't forget something.
The manufacturability.
Yeah, I mentioned it. Anyway, so actually it was the tower resonance that was driving critical condition at the end. So we could not go one step further. So the design is still conservative from the point of view of the constraint on mudline plasticity. But we gain 4 orders of magnitude on the annual failure probability, so huge gain in material. That was not so necessary in this case. You can convert this because we communicate on, on the mass reduction and so on capex. That's nice. We could equivalently say, okay, we gain 4 orders of magnitude on the failure probability. So we can take this and convert this in terms of lifetime extension for the existing actually wind farm, because the site is already built. So what we could say is that with the simplification of the project, because our model of the wind turbine is not the perfect image for confidentiality reasons of the industrial one, but it's very representative, but not the perfect one, of course. Wang, you contradict me if I say something more. But you can convert this 4 orders of magnitude gains in terms of many years of lifetime extension. So this could be also interesting for you in order not only to make design, but also to make lifetime extension of your assets.
So you're making OEM's life more difficult.
I mean, everybody has got to that. No, but definitely they are our friends. We want to work with them. So welcome on.
That's good.
I suspect there's also a little bit of tools have evolved since T-Site was designed. So perhaps the 20% is a fairly big number because of that evolution of the process, and probably 8 to 10% might be more like what you'd expect now. But it's still valuable.
Sure. No, I agree. Definitely.
Some of it could be simply that, also there's a process of iterative process of this design, which we actually had, with us, the design of the tower, design of the monopile, and the wind turbine properties. And then at the time of design, there was one team in I think Siemens that were working on the load assessment of the turbine, and then providing some inputs to at that time maybe it was EDF or some foundation designer that used this information and then try to do their own design of the monopile and the tower. And then I even don't know if the tower was like a generic tower or it was site optimized. But nevertheless, there was this iterative process where maybe people were also you cannot be so efficient as if you have all the information in one place and do it. And then again, also this other around the knowledge on environmental conditions. I mean, they also didn't have it at that time. Now they had, but maybe not with the numbers we know now, because now we have several years of actual data from the site. And again, that's also uncertainty, which you get penalized for more uncertainty. That's how it is. All right. Yeah. Anyone else? More questions? I know it's probably already tiring, right?
Yes, and just maybe may I ask a last question? That could we have, I will say, a point of view about representativeness of the audience? I will say where you from? Because we understood that some of you, for instance, are involved in offshore wind, but just to have an idea, maybe just the first idea of who you are.
So basically, I'm from English. Anyway, it's part of the English Europe. Lithuania, Latvia, Estonia, Poland, and so on.
Okay.
So we are going to self-develop. We're expanding very quickly. Just on renewables, will be 800 people for renewables in 2 years. And so we are focusing on wind, onshore, offshore, plus photovoltaic farms and battery energy storage. So it's super important for me as well how we can transfer this knowledge to onshore as well.
Okay.
Because onshore is still it's our core business. And we are from development, installation, construction, O&M, and we are selling energy.
But from the investment point of view,
from investment in the end.
Okay.
Owners of the sites.
Okay. Holistic point of view. Okay.
Do we have some OEM representatives here?
I think they run away.
Yeah.
So we have some, actually, we had, of course, the list of people that registered, and there was a lot of, I think, operators and some other asset management, or I would say, yeah, we're looking at environmental conditions, site assessment. So, how are you also, are you all wind turbine owners, or somehow apart from you, are the others can, yeah? How many are
Offshore wind foundation designers.
designers? Okay, nice.
Okay. Which companies?
With us.
Those two.
So I'm from StarCraft in Norway, so we are developing the.
So StarCraft and Ørsted, can I ask if you get the integrated design, or do you still iterate with the, or is it a secret?
I'm not Ørsted, I'm Wood-Pilsted.
Wood-Pilsted, yeah. So, but when you do the foundation design, do you still iterate with the OEMs, or do you get enough information to actually do the integrated design?
So early stages, we do our own internal load assessment. So we do our own integrated load assessment. Then we talk to the OEMs and do that exchange piece. So yeah, there's still an exchange. I'd say it's a pretty smooth process now. Certainly with all the major OEMs, and our numbers are not far off what they get. So we don't know anything about the controller. That's usually quite a big part of it. But yeah, we get it pretty close.
But you get the properties of the turbine. You get the
We get the load outputs.
You get load
So
outputs.
it's load exchange.
It's a load
Yeah.
exchange. Not
There's
the
stuff that
model
they need
exchange.
to keep with themselves.
That's something
makes
we,
sense.
I think one thing we've been always thinking about, maybe also in this project we've been discussing, and in other situations, is these more machine learning based tools, if there's any way to facilitate the model exchange. So maybe you don't get the full turbine model, but instead you get like a package surrogate model that can actually be a similar,
That's also inside the project, actually.
Yeah, we have that.
That was a real issue throughout the collaboration. Basically, no one was going to share models with anyone else, basically. So they ended up all using our surrogates because that could be shared easily. So we trained it on someone's model, and then this was used as a proxy for the real stuff to develop the methodologies, and then the methodologies were in the end finalized. But I would say, yeah, that was kind of a different way to use machine learning or surrogates than it's usual.
And it was the same for us between IPN and DNV. Actually, we diagnosed exactly the same issues. So the idea is that we were able to exchange information by means of the Gaussian process information. Yeah.
I think I more or less interrupted someone, by the way, when you were trying to say where you're
Yes,
from.
we are from Iberdrola.
Oh, okay.
I am for other teams. I am in the wind resource team. So sometimes it's difficult to find the communication between the different teams and knowledge, or better know what they need and what we can provide to them. Sometimes we act as independent teams with not much communication. This makes this more difficult. And also OEMs are quite very transparent.
But that kind of also tells me that probably I would have hoped to some extent that these 20% reductions we see, that maybe they have disappeared by now in terms of new tools and knowledge and new methods. But maybe we still need some, maybe there's still way to go, or more to do if processes are still a little bit, as you said, smooth, but still they're closed. The OEMs are not very talkative. Any other would like to share where they are from?
The same part.
Oh, okay, that's a big representation.
The different countries as well, so maybe trying to obtain as much information as we can.
Okay. Thanks for joining. Yeah, anyone else?
I'm a researcher from Australia, but doing related work on structural liability. So very interested in the surrogate model techniques.
Did you come from Australia to see this presentation?
Yeah, I have to be careful how I answer. Yes, I did. It's a part of a tour that I'm doing.
Yeah, yes, okay. That's
Yeah,
also
really interesting.
appreciate the effort to join.
You're not the only one from Australia. There was another two representatives from Australia.
Oh, really?
Yeah. And I was really surprised as well. I was like, that's quite an effort to come all the way to you.
Fancy the Guinness.
Oh,
Yeah, yeah. That's why yesterday evening. Yeah.
We have some people from the back row. I don't know, would you like to also share where you come from?
Sure, I'm from Exodus Group, so we're offshore consultants. So work a lot in oil and gas, but I work for the department. But we work quite a lot with early stage projects, particularly LCOE institutions as well. Interesting to see work.
I'm a PhD student from Trinity College. I did gene analysis. So we both are from the same research group, and I was looking at the surrogate models and using machine learning for developing various models for site specific.
Is your name Shubham by any chance? No?
Yeah.
Yeah. I'll have to read your PhD thesis.
So no pressure.
No, it's yeah. I was good to be one of the examiners. So thanks everyone. I don't know if you still are. You can also maybe. Oh, sorry. Yeah.
I'm from a startup from Austria, Inmox.
Okay.
And we are doing maintenance. And
Okay.
we are focusing on the gearbox. We are also developing our own sensor. It's a magnetic sensor that detects materials, so wear particles in the gearbox, like the size or the material, so we can say if it's from the bearing or from gears, and then you can do better repairs and you reduce downtime. So, and I was doing before also particle physics and data science, and it was also interesting.
Any gearboxes for Nordics machines?
Oh, the same in G and one of G, but then investors and knowledge. They're using the same.
Yeah. So we did not too much of, let's say, gearbox modeling. Actually, that was something we had like bearings versus gearboxes because we had the work package on components implementation, and then we need to rely to large extent on publicly available information. Otherwise, you can't. Let's say also then, if you start getting into confidential information, then there's less you can publish. So for that reason, we chose to use the bearing as the main, let's say, study exercise.
But we have very little information, I have to say, from OEMs. And we are mainly working with operators, but we have a physical approach. So our sensor, so maybe we don't really need that.
Yeah, that's yes. I think also our colleagues here from Equity have a lot of work on reliability, or maybe more data driven. I don't know. Maybe both. I assume both, right? Both physics and data.
Yes.
Yeah. So there is like the last thing we wanted to figure out is how to also have another way of feedback or further discussion engagement. Now I guess everyone is tired, and late. So if you also just want to tell us what you think, or also fill it in here. Here, if you fill it in, it's like legally binding. It's in there, but yeah. So. But otherwise, I don't just write something, or if anyone just wants to share what you think is, how can do we want to engage further do you just want to go and look at the website and read the results and download the tools, or is there any other types of follow-up activities that may be relevant? Any other things? Anything?
Maybe it's going to be a silly question. So I'm representative of renewable, but I'm not from the engineering background. So I'm representing the planning function, which is gonna hopefully help to bring all of this together. And I've been through all of these discussions today and yesterday, and one question in my mind was, do we have any specific, the standards or something like that can be utilized for between different projects, different wind farms, that we can actually benchmark ourselves against, so have like guidelines? Because it seems there is so many like new technologies, ideas, numbers, and I'm like, okay, it's a great number, but how do I know if it's some specific statistics you can go by? And us as a new company who's really rapidly growing, it's again, when do we potentially, can start from? So do you have any information maybe on that?
That's I can try. I can also maybe follow up on that. I really, I think that's a really good question or really good comment. And we have also been thinking about benchmarking as a way, further impact or making it also easier for people to say to compare things. And we have tried to do a few things like. There's actually a data set, like benchmark data sets or like openly available data sets. And I think in general in the wind community we have a few reference turbine systems. For example, there's like these IA tasks that develop. I mean, we were using actually, and this is extremely useful, this reference 15 megawatts turbine system. This is a reference system which the entire community can access and use. So I think overall I'm really much into, doing similar activities, and then so I think for this one it's maybe not so much reference turbine systems. As I said, this is maybe covered by other tasks, but then you have maybe some reference data sets, benchmark data sets, or benchmark reference use cases where you can actually demonstrate the entire workflow of getting to a certain place, surrogate models. And I think Stefano, you are willing to answer more.
I wanted just a little semantic thing. So there are two ingredients in a benchmark, or three ingredients, let's say. One ingredient is the test case, the case study, basically, that you want to benchmark. One is pretty easy, it's the competitor, basically, you want to benchmark, the different approaches you want to benchmark one against each other. And well, the third one is, let's say, the performance measure. Let's say a COE is a very well known one. Now, the problem is the following, that the methods and the tools are, I would say, almost 100% freely available out there. So everyone can download, access, and do anything with the tools. Problem is the test cases. As Nikolai is mentioning, there are some open data sets that are probably designs from 10, 15 years ago that have been out there because they're only one publicly available. So my point to you would be, I like the question, but I think you're asking to the wrong audience. You're asking to the wrong people. You should ask to the OEMs and the clients. How do you standardize or benchmark such a thing? Every one of us would be happy to be playing with the real toys and to compare, and because we don't know ourselves, we know
you're scientists. You're scientists.
We're scientists. We do stuff. We are happy for everyone to test and prove us wrong or right, but we can't do that.
Yeah, that's a really, really good point, like I said, because obviously, as we as a kind of, example, startup, you're trying to understand what information do you need at which stages of development, execution, or handover to OMs. And I came from a different background completely, not from the wind or solar at all. And obviously knowing that problem statement, that communication on the data that is actually, states with the OMs probably will help to, I don't know, to someone like me, and hopefully our renewables group maybe to target, that specific, I don't know, problem, issue, opportunity. I would say maybe opportunity, because I would think that our OEMs can maybe benefit of actually collaborating maybe more as well. Because I think that's how the innovation and the ideas come. No, but I think at least you gave me some sort of direction that me as a non-engineering person can.
It's not only OEM implementation, I would say. We are talking a lot about surrogates, and the point is that when you are making surrogates, you are making you have this part in which you validate the surrogate on synthetic data, let's say, and then you have this significant stage at which you want it to work. the real world with noise and all these perturbations that is that could put in phase some of the methods sometimes. And so we need it's also concerning operators actually, because actually the more we have real data from the assets, the more we can challenge the methods that we are developing in order to check they are really robust. And the point is that we are developing some methodologies on open project like this. We are making benchmark in IEA task. Maybe oldest one was 33, 47, I guess, with the comparison of servo-hydroelastic models leaded by NRL, by Jason Jodman and Amy Robertson stuff. Now you have the wall, also comparison of wake models in the wake bench, I guess, exercise, stuff like that. But the point is that at the moment, we need, when we go to the exercise of Hiperwind, to conform the methodologies to some real assets in terms of power prediction, design load components prediction, so going to all this validation of the digital twin activity. And currently this is done by some companies like DTU, myself, with IFP Energy Nouvelle, or our spin-off, Genix, or others, EPRI, or I don't know. But this is done in terms of confidentiality perimeters with some clients, and generally we cannot communicate on this. So the point is that we have some advance, some progress, but it's something that is not shared because we have some confidentiality. So that's it.
But I also think that that's because there's competition between developers, and developers like to take some of this stuff and have it as their knowledge to compete in.
I agree, but the point is that it's also introducing a competition between the researchers and not only the developers. And that's become problematic because if we put many years in order to have some leverage of solutions, think about the floating. I mean, we are far from answering all the questions that needs to be solved if we really want to have the floating that is, I would say, fully operational in the world one day. And if we stay like this, will it really, solve all the issues? I don't know, because probably we could find something that is much more efficient if we go toward the Hyperwind. We progress because we are really collaborative between ourselves, fully exchange of information, of expertise, etc. So people like Stefano, Nikolai, Alexio, etc., they exchange very closely on the same project. So if we stay with something that is very, closed in terms of information, it will take many, many years to progress. So that's the point.
But the one idea maybe we can take away for the next year, or there was an email just now after the conference had finished, and they was asking, okay, what topics would you like to add to the next year conference? And I think, maybe it's a good opportunity for us to maybe say, okay, supply chain or OEM, they could become part of, those discussions, because if this is the problem statement, then maybe we need to try to get those guys, and some of them, the brave ones, because I'm sure not everyone is really protective about information.
No, I agree that supply chain should be. Definitely, with the recent years, it was not the case, at the beginning of the project. So we were elaborating a scope, it was not the same context international 4 years ago. But definitely we had to write the project now, yeah. Right.
Thank you very much, it's very useful.
No, you're welcome.
I suggest thanks everyone, but I can see that we are also getting fewer and fewer, and we passed time. It's been, I guess, time for everyone. And I hope, although that you get some useful experience, and thanks everyone for joining. And also thanks, guys, very much.